So before we talk about derivatives, we got to talk about what is average rate of change. This is the most important thing to all of calculus, is average rate of change. What is it? Average rate of change is just the slope, right? Everybody's good with that? Average rate of change is just the slope?
Yes, sir.
All right, perfect. So sometimes on the AP test, they will ask you about the average rate of change of something. Don't get all caught up in trying to find a derivative or doing something weird like the mean value theorem for integrals or something. The average rate of change is just the slope. So if I want the slope between -1 and 3 of this, what do we end up doing? Plug in 3, right? 3 cubed minus 3 minus -1 cubed minus -1 all over 3 minus -1. And what do we get? Some number? 24 minus, what is that? That's, what is that? -1 plus 1? 24 minus 0 over 4. We get 6. Right? Average rate of change is just the slope. Yes?
Yeah.
All right, good. So what we're going to do is we're going to take some arbitrary function here, the function f of x, and we're going to find the slope of the secant line between these 2 points, or we're just going to find the average rate of change between those points. And so we should note that it should be the second y value minus the first y value. So f of x plus h minus f of x all over x plus h minus x, right? Which gives us this thing here, f of x plus h minus f of x all over h. And what do we call this thing?
Difference quotient.
Yeah, this is called the difference quotient. And the difference quotient is the single most important thing to all of calculus, right? The difference quotient, because that's where derivatives come from. So when we're looking for these average rates of change, right, we might become more interested on a smaller and smaller and smaller and smaller interval until that interval becomes almost non-existent, until that interval becomes 0. And so when we turn that interval, the interval between x and x plus h, right, if we can make this shrink down so that it becomes very close to 0, that should be giving us the slope of the function itself at that exact x value, right? The slope of the tangent line rather than the slope of the secant line that goes through 2 points of the function. It should become a slope of a tangent line. All right, everybody good with that? Hopefully. And so how do we turn that interval into a 0? Because if h is 0, like, right, this distance here is h, right? To go from x to x plus h is h units. If h becomes 0, we have a problem, right? We end up with 0 over 0. So how do we deal with that? We deal with it with a limit. That's right, Derek, a limit thingy. So what we'll do is we will make this into the limit as h approaches 0 of f of x plus h minus f of x. And so I'm skipping a bunch of pages. We want this limit right here. The limit as h approaches 0 of f of x plus h minus f of x all over h. Good? Yes, no, maybe?
Yeah.
All right, this limit right here gives us the slope of the tangent line. I'm not going to even do this problem. Just want to talk about it because this should be familiar to most of you here. And this is the slope of the tangent line at x. This is the limit definition of the derivative. So we want to know that this limit is the definition of the derivative. The derivative is the slope of the tangent line at any given value of x. I am not going to have you go through and do any of these problems where you have to like write out these long drawn out limits. And you don't have to do any of those. Everybody good on shrinking that interval down so that h is 0, so that rather than having a secant line, we have a tangent line, and that the slope of that tangent line is equal to this limit.
Will this show up on the AP test?
It will sort of, maybe, in the multiple choice sometimes. They'll give you something like, you know, they'll put a question in that's like, what's the limit as h approaches 0 of, you know, the square root of 4 plus h minus 2 over h. And you'll need to recognize that f of x is the square root of x, and that x is equal to 4, and this becomes the square root of x plus h minus the square root of 4 all over h. And you could say this thing is equal to the derivative of root x at x equals 4. So it shows up in the multiple choice like this, but you don't even have to necessarily even recognize that that's the case. I mean, it's good too, because then it's just really easy, because if you know the derivative of root x is 1 over 2 root x, just plug in your 4 and you get a fourth. If you recognize that. But if you don't recognize that and you plug this in, you get an indeterminate limit, and then there's multiple different ways to deal with it anyway. You could use L'Hopital's rule, you could multiply by the conjugate, all that good stuff. Does that answer your question?
Yes, thank you.
Yeah, it's sort of, I mean, it could show up. There's not always one of these in the multiple choice, but there's other ways around it if you don't recognize it. Cool. All right. I don't think I wanted to talk about any of the rest of this stuff, but make you do any of this. No, definitely not. Cool. So we're going to realize that this limit is the derivative, and that the derivative is the slope of the tangent line. And we're going to really, really quickly now go through the basic rules of our derivatives. So the first rule for derivatives is the derivative of a constant is 0. No matter what, take the derivative of any constant, you get 0, because what's the function? The function is just a constant, right? So this ends up being a constant minus a constant, and they end up being the same constant. And a constant minus a constant is just 0. 0 divided by h is 0. So we end up with the limit as h approaches 0 of 0, which is 0. The derivative of any constant is 0. Derivative of 7 is
0.
0. The derivative of negative 13 is
Probably 0.
yes, probably 0. And we'll note that that makes sense, because remember, the derivative is the slope of the tangent line. And if I have a function that is just this constant, it's just a horizontal line here, what's the slope of any horizontal line? Ought to be 0. And so the derivative, the slope of the tangent line, ought to also be 0. Good or no? Yeah? No? Good? Bad?
Good.
Indifferent? Good. Okay. Next rule that is important is the power rule. Okay. Our power rule just comes from using the binomial theorem to expand out this x plus h to the n into this horrific looking term here. You'll all agree with me that that's the correct expansion, because you all know the binomial theorem so well. But what will we note happens if we try to evaluate this limit? First off, some stuff cancels, right? What cancels? What cancels in this big limit here?
The first thingy and the last thingy.
Yes, very technical there. The x to the n and the minus x to the n cancel. And what is left in each of these other terms? They all have
H.
some sort of h in them, right? And so if we factor that h out and cancel it down here, we end up with n x to the n minus 1. And then up here, we end up with a bunch of other terms. I'm just going to write a bunch of terms with h in them. And if we're looking for the limit as h approaches 0 of n x to the n minus 1 plus a bunch of terms with h, what happens to those bunch of terms with the h's in them? They all become 0. And the derivative of x to the n is n times x to the n minus 1. Okay. Power rule, very important rule. Yes, everybody remembers the power rule for taking derivatives? Good. The derivative of x to the 7th, f prime of x, if f of x is x to the 7th, is? This is where you just really
7x to the 6th.
All right, good. And x to the 4th?
4x to the 3rd.
All right, and x to the 50th?
50x to the 49.
All right. It's like we remember the power rule. That's good. All right. We should know that the power rule can be extended not just for whole numbers, but for any real number. So what about the derivative of x to the negative 1?
Negative x to the negative 2.
Should be negative x to the negative 2, or we could write that as negative 1 over x squared. What about x to the 3/2? Should be
3/2 x to the 1/2.
3/2 x to the 1/2. What about x to the negative 4? Should be
Negative 4x to the negative 2.
all right, and root x should be
1/2 x to the negative 1/2.
right 1/2 x to the negative 1/2 if we make that root x and x to the 1/2. And often we'll write that one as 1 over 2 root x. Yeah. Good or no? All right. Easy ones here, right? X to the 2/3 plus 4x to the negative 3rd should become what?
Two-thirds x to the negative 1/3 minus 12x to the negative 4th.
Perfect. And this last one here. Should be what?
X to the negative 4/5 plus 10x to the negative 6th. Plus 6x to the 3rd.
Everybody agree with that? Basic power rule stuff, right? Okay. All right. We good or, well, let's do these two because these ones are written in an unpleasant way. What should this first one become?
1 over 2 root x.
1 over 2 root x. And then this is 5x to the 3/4, right? So that ought to become plus 15/4. What?
X to the negative 1/4.
And this last one should become minus
1/10 x to the negative 9.
all right. Good. Everybody good? Easy. And down here, x to the negative 1/2 ought to become negative 1/2 x to the negative 3/2, and then plus 15x squared. Everybody remembers how to take a derivative. Everybody is okay with taking a derivative, a simple derivative with the power rule. Yeah? All right. What are the first 4 derivatives? Just so we remember our notations. We have f of x. The first derivative is f prime of x, which is
6x to the 1/2.
Second derivative, f double prime, right? Should be 3x to the negative 1/2. Third derivative, we still write the 3 primes. That one should be negative 3/2 x to the negative 3/2. And a fourth derivative for all after 3, we just put the number in parentheses. 9/4 x to the negative 5/2. Everybody good? Our basic derivatives we're all okay with. Okay. All right, we're going to skip that last page there. That's not where I wanted to be. All right. We should be familiar with the product rule. I'm not going to prove the product rule. If you want to figure out how to prove the product rule, it's pretty straightforward. You just take the limit of a function times another function and add these terms in, add and subtract both of these in the numerator, and then you can separate into different limits. But we want to know the product rule. So the product rule says the derivative of one function times another function is the first function times the derivative of the second, plus the second times the derivative of the first. Right? The product rule. So you have to use it anytime you have a product of two different functions. So, well, you don't have to, because we could distribute these through. But let's use the product rule to differentiate this. What should f prime of x be according to the product rule? It should be the first function times the derivative of the second function, which is
2x.
2x, good, plus the second function times the derivative of the first function. And we could, if we wanted to, simplify all this out by distributing it all and combining like terms, but I'm going to say this is good enough for us right now. You could all distribute that out and combine like terms. I hope.
Indeed, we could.
Yes.
Spectacular. All right. In that case, let's move on to the quotient rule. Quotient rule says that the derivative of a quotient of two functions ought to be the first function, I'm sorry, the bottom function divided, bottom function times the derivative of the top function minus the top function times the derivative of the bottom function, all divided by the denominator squared. And I'm not going to go through and prove the rule. If you want to, go search online and find the video for it. But you do a very similar thing as you would have done with the product rule. So anytime you have a quotient of two functions, you need to know the quotient rule, v du minus u dv over v squared. So if I wanted to differentiate x squared minus 1 over x squared plus 1, what should f prime of x be? It ought to be v times du minus u times dv over the denominator squared. And let's simplify this one. What does that come out to if you simplify it? Yeah, 2x cubed plus 2x, and then minus 2x cubed plus 2x. So we got 4x over x squared plus 1 squared. Good or no?
Great.
All right, good. And then lastly, for these basic little rules here, we've got the reciprocal rule. The reciprocal rule is just an extension of the quotient rule, but it often makes things easier to differentiate. If you have 1 over a function, you can just turn that into the opposite of the derivative of the bottom function divided by the denominator squared. So this is another good rule to know. easily proven if you start with the quotient rule and just have your upper function being the constant, you'll find that this is what you get every time. So what do we get if we wanted to differentiate 1 over 2x cubed plus 5x?
6x squared plus 5 over the quantity of 2x cubed plus 5x squared.
No,
Negative.
Negative.
negative of that. There we go. Right, just apply the rule and you're good. Right, the slope of the tangent line to 1 over 2x cubed plus 5x at any x value is negative 6x squared plus 5 over 2x cubed plus 5x squared. Easy enough? Hopefully. Hopefully so. All right. Now, we talk about why a derivative might not exist. So there's 4 possibilities for why a derivative wouldn't exist. The derivative might not exist if, or will not exist if the function has a corner, if the function has a cusp, if the function has a vertical tangent line, or if the function has a discontinuity. So 4 reasons why a derivative might not exist at a specific point: corner, cusp, vertical tangent, and a discontinuity. And that should make sense because remember that derivatives are just limits, and the derivative from the left and the derivative from the right would have to be the same. And in this case, they are not, nor are they in this case, right? And here, the slope of the tangent line is vertical, so it's got to be undefined slope, which makes the derivative undefined. Everybody good with that? All right. And sometimes they like to throw out these on the AP test where they give you a bunch of values and then ask you to find the derivative of some annoying function like u times v. So if I wanted to find the derivative of u times v at x equals 2, that ought to be u times v prime. We'll just write it this way. And that would be u times v prime plus v times u prime. And since we're looking for it at 2, we just evaluate each of these at 2. U of 2 is 3. V prime of 2 is 2. V of 2 is 1. And u prime is -4. So you get 6 minus 4 over 2. Just by applying their product rule. Good or no?
Splendid.
Great. And if we wanted to do u divided by v, that ought to be v du minus u and u derivative v over v squared. So v of 2 would be 1. U prime of 2 would be -4. U of 2 would be 3. And v prime would be 2 over 1 squared. Which would give us what, -4 minus 6 or -10. Easy enough?
Yep.
Cool. All right. Now, what we are not going to do is we are not going to go through and talk about all of the different rules for all of the basic derivatives that you need to know, like the derivatives of all the trig functions. We're not going to talk about the derivatives of like e to the x and the natural log of x and how we prove all of those. But what you do need to do is you need to go in and make sure you have them all memorized. So before we talk about the chain rule, I'm going to note that in the Google Drive, there is a folder called Other Documents, and in that Other Documents folder is the list of all the different derivatives that you need to know and be able to complete. Okay, so that includes the derivative of sine, cosine, tangent, secant, cotangent, cosecant, derivatives of e to the x, the derivative of a to the x, the derivative of natural log of x, the derivative of log base a of x, all of those different derivatives of all of the inverse trig functions, all that stuff. You need to know all of those. And I'm not really going to go through and prove all of them. I'm just going to expect that you guys go in, look at that sheet, and memorize all those derivatives. Everybody good with that? Yes, no, maybe?
Yeah.
All right. Cool. So let's then briefly talk about the chain rule. The chain rule works when we have a composition of two functions, and we can write our function as y equals something in terms of u, with u equal to something else. So like, you know, if I have y equals sine to the fifth of x, well, I can call this y equals u to the fifth with u equal to sine x. And the way you find this derivative is by taking dy du and multiplying it by du dx. And sometimes you might see it written in one of these two notations. This one I will often use also. I probably don't use this one as much, even though it's perfectly legitimate. I'll use this one and this one the most often. Okay. So if you can write it as a composition of two functions, you can use the chain rule to evaluate it rather than having to write this out as sine times sine times sine times sine times sine, and then having to do like a million applications of the product rule. So we are going to find the derivative of the sine of 2x, and we're going to use the chain rule to do it, and then we're going to verify that what we got is correct by using some trig identities. So this could be written as y equals the sine of u with u equal to 2x. Everybody good with that? Yeah, no, maybe?
Yes.
All right. So what's dy du? What's the derivative of sine of u?
Cosine of u.
Cosine of u. And what's du dx? 2. So we've got the derivative f prime of x ought to equal dy du times du dx, which is 2 cosine u. And since we're talking about f prime of x, it needs to be in terms of x, so 2 cosine of 2x. Okay. So anytime there's a function within another function, we have to use this chain rule. Now, we could have rewritten f of x, since what did we have? We had sine of 2x. That's equal to 2 sine x cosine x, isn't it? So I could have used the product rule with these as my two functions. And then I would have said that the derivative ought to be 2 sine x times the derivative of cosine, which is negative sine, and then plus the derivative of 2 sine x, which would be 2 cosine x, times cosine x. And what would that give us? It'd give us 2 cosine squared x's minus 2 sine squared x's. And we'd recognize that that's this if we factor out the 2. And that cosine squared minus sine squared is cosine 2x, which is exactly what we got doing it the other way. But the chain rule way is a lot simpler, a lot less chance to make a mistake, and a lot less trig identities to deal with also. Good or no?
Fantastic.
Wonderful. All right. So we haven't talked about this, but we should know that the, well, maybe you shouldn't know yet, but you should know that the derivative of a position function is a velocity function. Okay. So if we wanted to find the velocity function given the position function x of t is cosine t squared plus 1, all we'd have to do would be to take the derivative of cosine of t squared plus 1. And how do we do that? Using the chain rule. It's cosine of u with u equal to t squared plus 1. So this ought to be negative sine of u times 2t, or negative 2t sine of t squared plus 1. Good or no?
Yes.
All right. Okay, let's see. You guys do the next few on your own, just to make sure we're good on the chain rule. All right, I gotta go deal with my dog. This isn't gonna work the way I wanted it to. Oh well. All right, well, do this one. You've already done this one, haven't you? What did you get? If you differentiate sine of x squared plus x, that's sine of u with u equal to x squared plus x. So it'll become 2x plus 1 times the cosine of x squared plus x. And I would hope that pretty quickly you guys will be able to do those without writing out the chain rule steps. Hopefully so. Everybody good with that one?
Yeah.
All right. Take a look at this next one while I go real quickly deal with my dog. Hopefully we all already did this one. Yeah? No? Maybe?
I got x over root x squared plus 1.
Sounds great. So it should have been, since the derivative of root u, or this is root u, with u equals to x squared plus 1, should be 1 over 2 root u times the derivative of the x squared plus 1, and your 2 just cancel. Everybody good there? What about this one? How would you write this one as a composition of two functions? What would your first function be?
U to the negative third.
Yeah, we'd have this be u to the negative third with u equal to 4x squared plus 6x minus 7. So u to the negative 3, its derivative becomes negative 3, and then u to the negative 4. So that'll become 4x squared plus 6x minus 7 to the 4th. And then the derivative of our 4x squared plus 6x minus 7 ought to be 8x plus 6. Good or no? All right. Could we apply both rules, the product rule and the chain rule together? Hopefully so. All right, so you guys do this one on your own, and then we'll talk about it in a second. So this is 3x plus 1 to the 6th times the square root of 2x minus 5. Ready, go. The product rule says that this should be the first function times the derivative of the second. And so the derivative of that ought to be 1 over 2 root 2x minus 5 times the derivative of 2x minus 5, which is 2. And then plus the second function times the derivative of the first, which will be 6. And 3x plus 1 to the 5th. And then times the derivative of the 3x plus 1, which is 3. Using the chain rule on both of the derivative pieces. Everybody good with that or no?
Good.
Good.
Okay, now the important thing that we want to make sure we can do is get a common denominator, simplify this down, factor stuff out if we need to, in case we ever needed to figure out when this equals 0, when its derivative was, whenever this derivative was equal to 0, or whenever this derivative was undefined. So first off, to get a common denominator, cancel those 2's first, we'll need to multiply both of them by root 2x minus 5, which means this part's just getting squared and becoming a 2x minus 5. And so now, what do they have in common besides the same denominator? They have a 3x plus 1 to the 5th power in common, don't they? So it'd be good if we could factor that out, leaving us with a 3x plus 1 to the first plus 18 times 2x minus 5 all over root 2x minus 5, which would be 3x plus 1 to the 5th times 39x minus, what is that, minus 89. Oh, that looked horrible. 39 x minus 89. There we go. All over root 2x minus 5. So it'd be good to be able to simplify that down. Everybody okay with that? Any questions, any issues with the simplification or the derivative itself? All right. What about this one? Tangent cubed 4x. This ought to be y equals u to the 3rd with u equal to tangent 4x, right? So what should our derivative be? dy dx, I'll write it as f prime of x. F prime of x ought to be 3u squared times the derivative of tangent 4x, which tangent 4x, to take the derivative, we need to use the chain rule. U equals tangent v with v equal to 4x. So the derivative of that will be secant squared v and then times 4. So what do we end up with as our final derivative? 12 u squared, tangent squared 4x, secant squared v or secant squared 4x. So chain rule within the chain rule. Everybody okay with that? Hopefully so. All right. Last thing that we will do today, we'll have made it through 2 weeks worth of derivatives in like a day. So we want to show that the slope of every line tangent to y equals 1. Is that a 1? I can't see it. It's blocked on my screen. 1 over 1 minus 2x cubed is positive. So first off, to show that the slope of every line tangent to it is positive, we need to find a derivative. So what's y prime? This is u to the negative 3, right? So what's the derivative? Derivative ought to be negative 3 u to the negative 4 times the derivative of 1 minus 2x, or negative 2, which ought to give us 6 over u to the 4. And what can we tell about this? Well, 6 is always positive, and 1 minus 2x, whether it's positive or negative, when you raise it to the 4th power, this is always greater than 0. as long as 1 minus 2x doesn't equal 0. And do we need to worry about 1 minus 2x equaling 0 for our original function? No, because it's undefined. If 1 minus 2x equals 0. Good or no?
Good.
All right.